Hello, welcome back to my channel, my _exe. Today I'm going to look at a proof that log base 2 of 3 is indeed irrational, as well as a bonus problem or a bonus proof at the end of this video. So, hope you enjoy watching this video. Thank you. Alright, so for the sake of contradiction, we can suppose log base 2 of 3 is rational. Meaning we could rewrite this as a fraction m over n, where m and n we can suppose them to be relatively prime integers, or in other words, the GCD of m and n is equal to 1. And by the definition of logarithms, or well, we can just simply take the power of 2 to both of these equations. So we have 3 is equal to 2 to the power of m over m over n, and then we can take both sides to the n power. That will give us 3n is equal to 2m. However, notice quickly that by the fundamental theorem of arithmetic, this equation does not have any solution for m and n to be integers, or at least integers that are not equal to 0. Because notice that the right hand side has a factor of 2, while the left hand side does not. Similarly, the left hand side has a factor of 3, while the right hand side does not. So therefore, we have a contradiction. So therefore, our original assumption that log base 2 of 3 is rational is wrong. So therefore, log base 2 of 3 is indeed irrational. Now we can generalize this to, I would say, kind of like a general formula or a general proof for a similar type of problem like this. Alright, so here's the bonus problem, which is kind of a generalization from the previous problem, as I've said before. So we need to prove that log base m of n is irrational if and only if n cannot be expressed as m to the power of x for some arbitrary integer x. Right. Like our similar method before, we can suppose, for the sake of contradiction, that log base m of n is rational despite our condition of our question. So therefore, we can express this as a fraction a over b, where a and b are relatively prime integers. Well, taking this whole thing with base m, we have n is equal to m to the power of a over b. Therefore, we can take both sides to the power of b. That will give us n to the b is equal to m to the a. Well, this right here, by the fundamental theorem of arithmetic, notice that the left hand side is a factor of n, while the right hand side does not. Similarly, the right hand side is a factor of m, while the left hand side is not. Hi, this is post editing math _exe here, and I just want to say something important that I didn't include in that previous script. So why does this equation does not have any solutions given our condition right here? Well, if we suppose n to be expressible as m to the x, then we can replace this n with m to the x. And then we can just compare the exponents right here, and therefore we have a solution for this equation. However, if we have n to be unexpressible as m to the x, therefore we are forced to have n just to be its original way. So therefore we cannot really tell if n is expressible as something or not. And the key point here is that with this condition, there exists at least one prime number or one prime factor that is a factor of the left hand side, but is not a factor of the right hand side, or possibly vice versa. It is a factor of the right hand side, but this is not. And by the fundamental theorem of arithmetic, we arrive at a contradiction. Therefore, we have no solutions for A and B. So therefore, we have arrived at a contradiction because there is no integers A and B that satisfy this equation. So therefore, log base m of n is indeed irrational for our special case of this condition right here.